Okay, so some biochemical reactions that we would see with alcohols include oxidation of ethanol. So ethanol, as we mentioned earlier, is in your alcoholic beverages. That gets oxidized by a liver enzyme called alcohol dehydrogenase. So the DH there is for dehydrogenase. That will turn into acetaldehyde. Which is responsible for your hangovers. So if there's a lot of acetaldehyde sitting around in your system, that is what's making you sick. That can further get oxidized, again with the alcohol dehydrogenase, to form acetic acid, which you are familiar with, which is in vinegar. Both acetaldehyde and acetic acid can get oxidized, and these are both detected by breathalyzers. And a fatal dose is 200 mils. "750 mils of 80 proof liquor contains 300 mils. So if you were to drink an entire 750 ml bottle, that would be more than enough to kill you. Methanol can also get oxidized by alcohol dehydrogenase. That forms formaldehyde. Which can further oxidize to form formic acid. Methanol is wood alcohol. That's often found in bathtub moonshine because it's not properly removed. If you ingest that, that is toxic, and ingesting as little as 30 mils can cause blindness. And 100 mils is fatal. So you don't want formaldehyde obviously sitting around in your system. That's what's making you sick. And further is the formic acid that is a metabolite of wood alcohol. So if you have methanol poisoning and you go to the emergency room, they're going to pump you up full of ethanol. Okay, so 30 mils causes blindness. 100 milliliters is fatal. And the reason for that is that formic acid that's sitting around in your system it's very acidic and it's not good for your system. If you ingest wood alcohol or this methanol and you get poisoned from it and you end up in the emergency room, they will have you ingest more ethanol because there is a greater affinity of alcohol dehydrogenase for ethanol than there is methanol. So it's 10 times the affinity. So if you have methanol poisoning, they're going to pump you up full of ethanol. This is the structure of ethylene glycol, which is what is used in antifreeze commonly. It's colorless, odorless, but very toxic. This is also oxidized by alcohol dehydrogenase. A 30 ml dose is lethal. The treatment for this poisoning also is ethanol, but when you do the oxidation here, you're going to end up with oxalic acid, which is toxic. Oxalic acid is also found in rhubarb leaves if you eat those. Okay, so for this practice problem, we see an alcohol with an aldehyde and another alcohol. If we use chromic acid here, excess chromic acid with acetone, this is going to oxidize everything. So this gets oxidized to the carboxylic acid, as does this. So we have primary alcohol here, secondary. So we get ketone, carboxylic acid, carboxylic acid. If we do the same reaction with PCC, this is only going to oxidize the alcohols. It will leave the aldehyde alone. So this primary alcohol becomes the aldehyde. So when we're doing multi-step synthesis involving carboxylic acids and alkynes or different functional groups, we have this extra tool in our toolbox now because we can go through alcohols and aldehydes very easily. So you can imagine using this synthesis through the aldehyde or an alcohol because we can do an oxidation to get to that point. But if we had an aldehyde, we can go directly back to the alkyne using 9-BBN and H2O2 with sodium hydroxide. Here we have a ketone and the alkene here, so we can imagine this can come from an alcohol because we're not losing any carbons, and we can get to the OH from the alkene. So this might have been a longer step synthesis or something that we couldn't achieve before without cutting off carbons, and now we have this ability to do so going through the ketones, aldehydes, or alcohols. So you can see the different strategies to get to these things. This is alkyne and alkene reductions, or ways to go back from alkenes to alkynes. And now we have these added reactions where we can go from alcohol to ketone, ketone back to alcohol, alcohol to aldehyde, or aldehyde back to alcohol. So these in this direction are oxidation reactions. This is a reduction, oxidation, reduction. If you look at what you can do with all the reactions that you know, our toolbox is open considerably. Now we can do things with ketones, alcohols. So these are all reactions that we'd seen up to this point, and we've now just added this part of it and then this part of it as well. These are what you should already know. The reactions in the quadrant that's not circled, those ones are from 225. These are the new ones here. If we're looking at different strategies here, I have a BR. I need to go to either the carboxylic acid or this ketone here. We can do that going through the alcohol. So you can first make the alcohol using sodium hydroxide. Follow that up. Here I have an aldehyde, so I want to stop the oxidation partway through, so I'm going to use PCC. Here, again, I use the same NaOH to get to the alcohol. I want to go all the way to the carboxylic acid, then I can use H2Cr2O4. If you need to add a carbon, you can do that by attacking the carbonyl with the Grignard to add this carbon here, and then you can oxidize after the fact. So if I want to add this carbon here, I can start by adding this part of the molecule. So I've seen 1, 2, 3, 1, 2, 3, add a Grignard. And then I'm going to add water, which will protonate that alcohol. So I'll draw the intermediate here. So this would be the intermediate, and then step 3 would be PCC, which would oxidize this back to there. Okay, in these problems, we want to figure out what their products are. If I have sodium borohydride, so this is going back to part A of chapter 13, sodium borohydride in the presence of an ester and a ketone. If you recall, sodium borohydride is the milder one. So this one will only reduce the ketone, and that will go to the alcohol. Everything else should stay the same. The lithium aluminum hydride is the stronger one, so this is going to reduce everything. All the carbonyls anyway. And then this will fall off in the process. If we now use H2 palladium, H2 and palladium, that will reduce the double bond. Alright, so you want to design a synthesis for the following molecule, starting from an alkyl halide and a carbonyl, using 5 carbons or less. So there's going to be different solutions that are possible. This right here has 5 carbons as it is. This also has 5 carbons. So I'm going to actually go backwards from this plus that Grignard. So if I do that, this is probably the most simple one, I think. So this would have to come from bromocyclopentane to make the Grignard. And the water. So that would be one way of doing that one. So you may have other answers that came up as long as you started with less than 5 carbons. You could have had an aldehyde here and done the Grignard twice. That would be a different solution to that as well. Probably unnecessary, but again, if it works, then it works.